At the end of this video, you should be able to describe situations in terms of frame of reference and solve problems involving relative velocity. Chapter 3, Section 4, Relative Motion. Frames of reference. If you are moving at 80 kilometers per hour north and a car passes you going 90 kilometers per hour north, to you, the faster car seems to be moving north at 10 kilometers per hour. Someone standing on the side of the road would measure the velocity of the faster car as 90 kilometers per hour north. This simple example demonstrates that velocity measurements depend on the frame of reference of the observer. Velocity measurements differ in different frames of reference. Observers using different frames of reference may measure different displacements or velocities for an object in motion. That is, two observers moving with respect to each other would generally not agree on some features of the motion. Consider a stunt dummy that is dropped from an airplane flying horizontally over Earth with a constant velocity. As shown in Figure 4.1a, a passenger on the airplane would describe the motion of the dummy as a straight line toward Earth. An observer on the ground would view the trajectory of the dummy as that of a projectile, as shown in Figure 4.1b. Relative to the ground, the dummy would have a vertical component of velocity, resulting from the freefall acceleration and equal to the velocity measured by the observer in the airplane, and a horizontal component of velocity given to it by the airplane's motion. If the airplane continued to move horizontally with the same velocity, the dummy would enter the swimming pool directly beneath the airplane, assuming negligible air resistance.
When you measure the velocity of an object, your results depend on your own motion as well as the motion of the object. Imagine a plane flying overhead dropping a crate. If you're standing on the ground, the crate will be seen to move sideways at the plane's velocity while falling down. However, if you measure the crate's motion from the airplane, it does not move forwards or backwards from your point of view. The crate falls straight down in this frame of reference. To really understand this, pretend that you are in a completely vibration and wind-free airplane. You might have no idea you are moving if there was nothing nearby to compare your motion with. No frame of reference is special or preferred over any other. Therefore, all motion is relative. When you measure an object's velocity, you are really measuring its velocity compared to your own. All motion is relative.
Relative velocity. The case of the faster car overtaking your car was easy to solve with a minimum of thought and effort, but you will encounter many situations in which a more systematic method of solving such problems is beneficial. To develop this method, write down all the information that is given and that you want to know in the form of velocities and subscripts appended. V sub SE is equal to positive 80 kilometers per hour north. Here, the subscript SE means the velocity of the slower car with respect to Earth. V sub FE is equal to positive 90 kilometers per hour north. The subscript FE means the velocity of the fast car with respect to Earth. We want to know V sub FS, which is the velocity of the fast car with respect to the slow car. To find this, we write an equation for V sub Fs in terms of the other velocities. So on the right side of the equation, the subscripts start with F and eventually end with S. Also, each velocity subscript starts with the letter that ended the preceding velocity subscript. So V sub Fs is equal to V sub Fe plus V sub Es. The boldface notation indicates that velocity is a vector quantity. This approach to adding and monitoring subscripts is similar to vector addition, in which vector arrows are placed head to tail to find a resultant. We know that V sub Es is equal to negative V Se because an observer in the slow car perceives Earth as moving south at a velocity of 80 kilometers per hour, while a stationary observer on the ground, Earth, views the car as moving north at a velocity of 80 kilometers per hour. Thus, this problem can be solved as follows. v sub fs is equal to v sub fe plus v sub es is equal to v sub fe minus v sub se. So v sub fs is equal to positive 90 kilometers per hour north minus positive 80 kilometers per hour north, which is equal to positive 10 kilometers per hour north. When solving relative velocity problems, follow the above technique with writing subscripts. The particular subscripts will vary depending on the problem, but the method of ordering the subscripts does not change. A general form of the relative velocity equation is v sub ac is equal to v sub ab plus v sub bc. This general form may help you remember the technique for writing subscripts.
Consider a fast car passing a slow car on the highway. The fast car is traveling at 70 kilometers per hour and the slow car is traveling at 40 kilometers per hour. It is easy to see that the relative speed between the fast car and the slow car is 30 kilometers per hour. That is, a passenger in the slow car who didn't realize that his car was moving would see the fast car coming up from behind at a speed of 30 kilometers per hour. For simple situations like this, common sense will usually give the right answer. When things can move in 2 or 3 dimensions, however, the subscript method is useful. First, write the velocity of the fast car with respect to an observer standing still on Earth as v sub fe. Next, write the velocity of the slow car with respect to an observer standing still on Earth as v sub se. In a moment, we will need to know v sub es, which is just the opposite of v sub se. It refers to the velocity of the Earth seen from the perspective of a passenger aboard the slow car. Since it is the opposite velocity, we give it a negative sign. If you want to determine the velocity of the fast car with respect to an observer on board the slow car, that label would be v sub fs. This equation will find that relative velocity. Notice that the first subscript of the first term on the right and the second subscript of the second subscript on the right make up the subscripts on the left. The middle 2 subscripts on the right agree. This allows them to disappear from the answer on the left. In this way, we can show the result we expected. Notice we could construct v sub sf, the velocity of the slow car with respect to the fast car, in the same way. Remember that v sub ef is the opposite of v sub fe. If we are trying to find v sub sf, write a term with the s subscript first and then finish with the f subscript. Once again, the middle 2 labels of the vectors we are adding must agree. This velocity is found to be negative 30 kilometers per hour. It is the opposite of the previous relative velocity we found because it is from a different frame of reference.
At this point, you should be able to describe situations in terms of frame of reference and solve problems involving relative velocity.